Hey friends, today we will learn how to create and start a thread. This is vital because threads let your programs handle multiple jobs at once, like fetching data in the background without freezing your app. So open your code editor and let us dive right in. Imagine you are reading a book while your computer downloads a file in the background. The download does not freeze your screen because it runs on its own separate path of execution, which we call a thread. We simply call this a thread. It is a lightweight process that handles one task at a time, and every Java program starts with one already running your main method. Let us write the code. We start with our main class and the main method. Inside, we define a runnable task using a lambda expression that prints a message. Next, we pass that task into a new thread constructor. Finally, we call start on the thread object. Notice what happens when we call start. The Java virtual machine kicks off a new execution path immediately. Our main method does not block or wait. It simply moves forward, leaving the thread to handle its own task in the background. You might wonder why we do not just call the run method directly. If we did, the code would execute on the main thread itself, giving us no parallelism at all. Calling start is what actually hands the work off to a separate execution path. You have just learned how to create a task and launch it on its own thread. Next, let us look at watching two threads interleave. Now that we know how to start a single thread, let us launch two of them and watch what happens when they run together. First, worker 1 grabs the CPU, then worker 2 jumps in, and they keep trading turns as their steps weave back and forth. If the loop finishes instantly, one thread might complete before the other even starts, hiding the pattern. Adding a short pause after each print forces the scheduler to switch threads, making the alternation visible on screen. Let us add the interleaving code to our main method step by step. First, we define a runnable, which is simply a task a thread can run. Inside it, a small loop loops 3 times, printing the current thread name each time so that when two threads share this task, we can actually see which one is speaking. Right after the print, the thread pauses, then sleeping for 100 milliseconds. That tiny pause matters because it hands the processor back and lets the other thread jump in, which is exactly what makes the interleaving show up on screen. Now we create our two worker threads from that same task, giving them distinct names so we can track each one as their lines mix together. With both threads prepared, they are ready to run. We start both of them and they begin running at the same time. Finally, back on the main thread, we call join on each thread to make sure main waits until both workers have completely finished before it moves on. We watch thread A and thread B competing for the console. Inside the loop, get name grabs whichever thread is actually running at that exact moment. Because the scheduler decides who runs next, we see worker 1 print first, then worker 2 jumps in, and we cannot predict which line appears first on the console. We picture the main thread approaching a join checkpoint, which leads to an all done state. The method acts like a checkpoint for the main thread, and it blocks and waits patiently until that thread finishes its entire loop before moving forward. You have now seen how two threads interleave their work and how join keeps main in sync. This unpredictable ordering is exactly what leads to the next problem we will tackle. Next, let us look at the race condition. Imagine cook A with a bowl, adding a spoonful of sugar into it, while cook B tries to do the same at the exact same time. When this happens in code, we call it a race condition. We have two threads, thread 1 and thread 2, and a shared counter variable. Thread 1 reads the counter, then thread 2 reads it too. Both increment and write back, so one update is lost. The counter is the shared variable that both threads modify without any lock. Now for the danger of shared state, and this is the heart of the whole problem. We keep everything inside main, and we declare a shared counter as a one-element array. Using an array here is a small trick. It lets both threads reach the very same value and change it. Then we make a runnable whose only job is to add to that counter again and again. Inside it, a loop loops 100,000 times, and on every single pass it does counter plus plus, one tiny increment. After the body, we end the loop, and then we close the runnable so the task is complete. Now we hand that identical task to two threads, inc1 and inc22, both pointing at the same counter. We start them both at once, so now they are racing, and then we wait for them to join, so main does not rush ahead. Finally, we print the expected total of 200,000, the number we would get if nothing went wrong, and right beside it we print the actual total we really got, which almost always comes out lower, because while one thread was reading the counter, the other was overwriting it, and those updates were simply lost. As we saw, without synchronization, the final count can be wrong. Next, we will fix this with synchronized. So how do we stop threads from stepping on each other? Java gives us one keyword, synchronized, and it lets just one thread at a time into the guarded section. Thread A wants to update, but it cannot just barge in. There's one shared lock and thread A reaches for it first. The lock guards the counter, sitting on top of that value so nothing else can touch it. At the same time, thread B is blocked, waiting on the same lock until it is free. Now the fix. First, we reset the counter to 0 for a clean run. We create one lock object to act as the gate. Then we loop the same 100,000 times, but this time we wrap it in a synchronized block and only increment inside it. Then we close every block. We make two fresh threads, we start them, and we wait for both. Finally, we print the fixed total, and we close main and the class. And that is it. One lock turned a broken count into the right one every single time. Thanks for watching and keep coding.